Hi, welcome to the second tutorial for Webots-Blockly. In the first tutorial, we showed you how to install all the necessary components to running Webots-Blockly. In this tutorial, we will get you started programming with Webots-Blockly. As you may recall from the first tutorial, to open up Webots-Blockly, first navigate to the project folder called Webots-Blockly that you downloaded off GitHub. Next, enter the worlds folder and double-click on the world that you want to work in. We will be using empty.wbt. When you open up Webots, you should be greeted with a screen that looks similar to what you see right here. In the first tutorial, we showed you how to reach the optimal window layout for using Webots-Blockly. So your screens should look pretty similar to this. To briefly introduce the various windows in front of you, right here is your world view. This is a view of the simulation environment your robot, right here, will be running in. As you can see, it can interact with the rectangular arena it is in and a box in the center. Up here are various buttons you can use while running the simulation. Down here is the console window, and this is where all print statements and displays get sent to. So you can see any compilation commands executed here, and then any print statements that you add using Webots-Blockly will also get printed to this window. This window to the left over here is the Webots-Blockly window. This is where you will be programming and dragging out blocks into this white space. All the blocks that you drag out to this white space will be translated into Python and displayed in this text output window right here. This text output window is not completely necessary to running your code, but it can sometimes be insightful to see your blocks in text-based code. Next up are some helpful buttons you can use while running your code. The first is your file name. You can change your file name from untitled to whatever name you want, such as my file, and when you click away, your file will be renamed. You can use the submit button to upload your code to the robot so that when you run your robot, the robot will execute the code you have programmed. Here is the save button, and it will save your file under your file name to a folder inside the project folder that you downloaded off GitHub. For example, I can save my file, and if I open up my project folder that I downloaded off GitHub, if I navigate to controllers and then Blockly programs, you will see that my file has been saved into this folder. So this is your save file for the code you have written. You can open up programs using the restore button. And from here, you can click on whichever file you want to load. For example, my file. Here is the reload world button. You're going to use this button to reset your runs and run updated programs. This button right here is the pause and play button. Use this button to play the simulation. You can also use this button to pause the simulation. As you can see, when I hit play, this timer over here will begin counting how much time has elapsed since you played this simulation. Before we begin programming in Webots-Blockly, there are first a few things you need to know. As with any drag and drop programming language, you can use these categories to drag out blocks in sequential order to create a program. This is very important. Whenever you create a program, your program must start with a start block, or else your program most likely will not work. From there, you can attach various blocks one after the other, like so. There are some blocks that allow you to attach blocks to the right of it instead of right below it. For example, I can use a print statement block, and then I can attach information to the right of the print statement. For example, I can attach a string that says hello, and this string will be fed into the block to the left of it, which is the print statement block. To get started with motors, there are first a few things that you need to know. In order to reference a specific motor, such as the left motor or right motor, we must create motor variables. This is just a regular variable that we assign to a motor. So, for example, I'm going to go to the variables category. I'm going to create a variable. I'm going to create a motor variable for my left motor. And then I'm also going to create a variable for my right motor. Then we have to tell the program which motor our variable corresponds with. To do so, go to the motors category and drag out a setup motor block. Use the drop-down menu to select a motor variable. I'm going to use left motor, and then type in the name of the motor that you want to assign to this variable. The left motor of this robot by default is left wheel. So if I type left wheel as such, this will assign this robot's left motor to my left motor variable. And I can do the same thing for the right motor. So I'm going to do another setup motor block, select the right motor variable, and type in right wheel. Now our motors are initialized and we can begin using them. I can use a set speed block to tell a specific motor, left or right, to go at a specific speed. I can assign a number here from negative 100% to positive 100%. Negative 100% is full speed backwards, and 100% is full speed forward, while 0 is a stop. So I can use the math category and drag out a number. I'm going to type 50%. This means that the motor will be going forward at half of its maximum speed. Then I'm going to drag out another set speed block for my right motor. I'm going to drag out another number block and assign negative 50% to my right motor. This means my left motor will be going forward half of the maximum speed, and my right motor will be going backwards half of the maximum speed. Therefore, our robot will be turning in place. Now, since we want this program to last more than a split second, we need to add a delay block. I can go to the time category and drag out a delay block, which will suspend the program for a specified number of milliseconds. Note that if I have a delay in my program, the simulation is not paused. The simulation will keep going. It's just that no more code is executed for the duration of the delay block, and then it will continue after the time is up. So I'm going to drag out another number block, and I'm going to delay for 100 milliseconds. Now, I want to run my program. The first thing to do is to save your code using the save block. Then, you can click submit to upload your code to the robot. Now, since my simulation is already partially played, I'm going to reset my simulation using the reload world button. Make sure that when you use the reload world button, your simulation is on pause. If your simulation is not on pause, then your simulation will automatically run after you reload the world. So I'm going to reload my world. I can discard changes. And then when I hit play, my robot will spin in place. And as you can see, my robot spins for more than 100 milliseconds because I never stopped my motors. So I'm going to add 2 more set speed blocks. I'm going to assign my left motor to go at 0. I'm going to assign my right motor to also go at 0, fully stopping the motors. Let's repeat the run process. I'm going to save my code. I'm going to submit it to upload it to my robot. I'm going to reload the world, making sure I'm on pause. And then I'm going to press play. As you can see, the robot spun for 100 milliseconds and then stopped. A very useful feature of motors is what's called an encoder count. As your robot's motors turn, they will keep track of how many degrees they've rotated forward using an encoder count. How this count works is, for every degree that your robot's motor rotates forward, the encoder count is increased by 1. For every degree that your robot's motor rotates backwards, the encoder count is decreased by 1. Each motor on your robot will have its own individual encoder count. So the left motor will have its encoder count, and the right motor will have its own encoder count. To use these encoder counts, I have a program that will make my robot move forward for 1000 milliseconds, or 1 second, and then it stops the motors. I want to print out the number of degrees that my left motor has rotated forward in this period of time. To do so, I'm going to drag out a print statement block, and I'm going to go to motors, and I'm going to use get encoders and attach it to this print statement. And since I want to get the encoder count of the left motor, I'm going to use my left motor variable. And what this will do is it will print out the number of encoders of my left motor. So I'm going to run my program, I'm going to save it, submit, and since my simulation is already reset, I can just hit play without reloading the world. So as you can see, my robot goes forward, and then it stops and prints out a value, 360.83, etc. This means that my robot going forward at half speed for 1 full second resulted in my robot's left motor rotating forward 360 degrees. Now, since both motors were going forward at the same speed, you can probably guess that printing out the encoder count for my right motor will yield a similar value. However, since both motors are not always going forward or backward at the same speed for the entire program, you have to be careful about which motor you want to get the encoder count for. Now, there are also times where you want to reset the encoder count. For example, let's say after I move forward, I want to erase all previous track of previous movement. So what I can do is I can reset the encoder count of my left motor. I can use the reset encoders block and specify that I want to reset the encoder count of my left motor. Note that resetting the encoder count of my left motor does not affect the encoder count of my right motor in any way. So what I can do is put another print statement, because after this block is executed, this get encoders of my left motor should return 0 because the value has been reset by this block. Since this get encoders came before this reset encoders, this print statement should still yield a value of about 360 degrees. So I'm going to run my program, I'm going to save my code, I'm going to upload it to my robot, and I'm going to reload the world with it on pause. I can discard my changes, that's fine. Now I'm going to hit play. And as you can see, my program worked as expected. My robot went forward for 1 second, then it stopped. Using these blocks, it printed out that my left motor rotated 360 degrees forward throughout this duration of the program. You can see this by the 360 degrees. Then it reset the encoder count of my left motor, and then it reprinted out the fresh encoder count of my left motor, which was 0 degrees. Now that we've finished the introduction to motors, we will now move on to sensors. The first sensor that we're going to work with is the distance sensor. The robot in this world comes by default with a distance sensor pointing directly to the right. This distance sensor reads in centimeters. To learn how to change the position, direction, or name, which we'll get to later, of the distance sensor, make sure you watch till the end of this tutorial. To use this distance sensor, just like with motors, we're going to have to create a new variable. This variable will represent our distance sensor. So when I create a variable, I'm going to name my variable dist sensor. Now this variable will be used to refer to our distance sensor. Drag out and initialize other sensor block from the sensors category. Select the distance sensor option and select your dist sensor variable. This second argument takes the name of the distance sensor. By default, the name of the distance sensor is distance space sensor. Simple enough. Now with this block, we've initialized our sensor and paired it with the dist sensor variable. Now we need to print out the value of a distance sensor. To do so, I'm going to put it inside an infinite loop. So I'm going to use a while loop, and I'm going to attach the number 1 to the while loop to indicate that I want this loop to repeat forever. Inside, I'm going to drag out a print statement, and then I'm going to drag out a getDist block. I'm going to specify my distance sensor variable. So what this program does is initialize my distance sensor, and an infinite amount of times it's going to print out the distance sensor of the distance of my distance sensor in centimeters. One important thing to note is you cannot use the getDist block unless it is inside or after a while loop. This applies to a lot of the other get values for the sensors, and we'll talk about that. But for example, this statement will be fine because the getDist is inside a while loop. This would, if I drag the print statement out, this getDist block would also be fine because it comes after a repeat while loop. Let's pretend this is not an infinite loop. However, this will not work because there are no while loops coming before this getDist block. You can try it for yourself, but the program will throw an error. So we're going to put our print statement inside a forever loop. And I'm going to run our program. So we're going to save, we're going to upload our code, we're going to reload the world, and discard our changes. And discarding these changes is just removing any changes we've added to this world, not our code. So for example, if you've moved the robot or changed your view, it will ask to discard these changes, not your code again. This code is dictated by the save button. So if you see the do you want to discard changes to this world, that's fine. Okay, now we're going to run our code. As you can see, our robot is printing out the value that our distance sensor sees in centimeters. So if I take this robot and I can hold shift and drag this robot around to make sure that it moves horizontally, and you can see that as I approach this right wall, my distance sensor readings decrease. And as I increase the distance between the robot and the wall, the distance sensor values increase. The next sensor that we're going to cover is the robot's light sensor. The robot has a light sensor that points straight down to tell us how dark or light the floor is beneath the robot. The light sensor returns a value from 0 to 255, with 0 being the dark end of the spectrum and 255 being the light end of the spectrum. To illustrate this point, I've opened up a new world. This is the light sensor box challenge world because it has these dark pads. Using a light sensor is very similar to using a distance sensor. I have to create a new variable for my light sensor. I'm going to call it light sensor. Then I'm going to go to sensors and drag out an initialize other sensor block. I'm already on the light sensor option. I'm going to specify that I want to use my light sensor variable. The second argument, like before, takes in the name of the light sensor. The default name of the robot's light sensor is light space sensor. Once again, this initializes the light sensor and pairs it with our light sensor variable. Just as with distance sensors, we cannot perform a get value on our light sensor until we are inside or have already completed a while loop. So I'm going to drag out a while loop. I'm going to make an infinite loop by attaching a 1 to it. I'm going to do a print statement. And I'm going to go to the sensors category. And I'm going to drag out a get light block. And I'm going to specify that I want to use my light sensor. I'm going to run my code, save, submit, reload the world. And then I'm going to run my program. As you can see, it starts printing out values. So 6 is pretty close to 0, indicating that it is indeed on a dark spot. Then once again, I'm going to hold shift down and drag around my robot. As you can see, when it moves off the tile, the values increase. And since there are white spots and there are also brownish spots, the values may change as you drag it around the floor. The next sensor that we're going to cover is the robot's gyro sensor. The robot's gyro sensor returns the angle heading of the robot. How the angle heading works is, for every degree that this robot rotates counterclockwise, the count will increase by 1. For every degree that the robot rotates clockwise, this count will decrease by 1. So, to use our gyro sensor is actually easier than the distance and light sensor. All I have to do is go to the sensors category, drag out an initialized gyro block, and pass in the name of the gyro sensor. The default name of the gyro is just gyro, all lowercase. Now, once again, I'm going to put my get block inside of a while loop as to avoid the error. I'm going to drag out a print statement, and I'm going to print out the get gyro values. As you can see, we do not have to create a variable for our gyro sensor. We only need to create variables for our motors, our distance sensor, and our light sensor. The gyro and the GPS, which we'll talk about next, do not require a variable. So I'm going to save my code, submit it, and before I run it, I actually have to make sure that my robot is spinning so I can actually get changing values. I'm going to set up my two motors. Right, I'm going to have to create two motor variables, as we talked about earlier. Specify left motor, right motor, left wheel, and right wheel. And then I'm just going to set my speeds so that my robot is rotating. So, by setting a positive value to my right motor and a negative value to my left motor, I'll be making my robot turn counterclockwise. So my angle heading should be increasing. So right motor goes forward and left motor goes backwards. Okay, now I'm good to save and submit. I'm going to reload my world. And then I'm going to press run. And you can see that my robot is rotating counterclockwise, and as it rotates counterclockwise, my angle heading constantly increases. As you can probably tell, there's no specified bounds on this value. This will go up until the maximum value a Python variable can store. So yeah, it is not confined from 0 to 360 or from negative 180 to 180. It's just from the negative max to the positive max. To illustrate the reverse point, I'm going to make it spin clockwise. And our values should now be decreasing. So I'm going to run. And as you can see, my angle heading decreases by 1 for every degree that my robot turns clockwise. And obviously, throughout the program, as your robot turns both clockwise and counterclockwise, the angle heading will increase and decrease throughout the program. The last sensor that we're going to cover in this tutorial is the robot's GPS. The robot does have an additional camera sensor, but we're not going to cover that in this tutorial because it is a little bit complicated. So the robot's GPS, the way it works is it returns the XYZ coordinates of the robot relative to its position at the beginning of the simulation. You'll see that in action later on. The way that it returns the coordinates is in a 3-element list. So you can explore this list category if you're familiar with Python lists. For those of you who are more familiar with C, C++, or Java, lists are similar to arrays except they can expand in size. So what we're going to do is we're going to initialize our GPS sensor using the initialize GPS block, and the name of the GPS is just GPS, all lowercase. Like always, we're going to use a while loop to avoid the error, and it's going to be a forever loop by specifying 1. I'm going to print out the value that my GPS returns. I'm going to save, submit, reload my world. Okay, now when I run my program, these are long decimals, but you can see that each one of these values are relatively close to 0 because this robot's origin position, the robot's position at the beginning of the program, is going to be the origin. Now, as I move my robot around, you can see the coordinates will start to change. So I can move my robot in this direction along the blue axis, and I can move my robot in this direction along the red axis. So to figure out what axis is blue, red, and green, all I have to do is move around my robot. So I'm going to move my robot along this red axis, and you can look at the GPS value. So the GPS returns X in the first element, Y in the second element, and Z in the third element. So when I move along this red axis, you can tell that the first element is changing dramatically, which is the X coordinate. Therefore, you can deduce that the red axis is the X axis. Then I can move along my blue axis, and you will see that the last element is changing most dramatically. So this blue axis is the Z axis. And then I can move along this green axis, and you can see that the middle axis is changing most, or the middle element is changing most. So green will be the Y axis. Now, as I said before, the GPS returns the XYZ coordinates using a 3-element list. If you want to access a specific element, a specific coordinate, so let's say just X or just Y or just Z, you can use the list blocks. So what I'm going to do is, instead of directly printing out what the GPS returns, I'm going to save it into a list variable. So my list, I'm going to set my list equal to get GPS values. And now my list is going to be a 3-element list containing the robot's coordinates. Now if I go into the list category, I can use the get block, which will retrieve a specific element of a list. I want to get it from my list. And since X is the first element, X has index 0, Y has index 1, and Z has index 2. So let's say I just want to focus on my X coordinate. I'm going to do a print statement. I'm going to print out the first element of my list, which is index 0. So this should print out the X coordinate of my robot. So I'm going to load this, save, submit, reload the world, discard my changes, that's fine. Now I'm going to run my program. You can see that as I change my robot's X position, the coordinate changes accordingly. So that is how you retrieve a specific coordinate of the GPS value. So there may be some properties about the sensors that are in by default in this world that you want to change. For example, the distance sensor by default is facing to the right, and you may want to change that. To do so, all you have to do is open up the scene tree. Go to Tools and click on Scene Tree, and it will open up the scene tree, which is a list of all the objects inside this world. You can see my robot, you can see the wall, and my arena, and etc. Since we're interested in the robot, hit the drop-down menu on the Define Robot Pioneer 3DX. Over here, go to Extension Slot, and under Extension Slot are where all the sensors are listed. So you can see there's a light sensor, distance sensor, GPS gyro, and camera. So we're going to dive into the distance sensor because that's what we want to examine. And first things first, I can change the name of my distance sensor by modifying this value using this box down here. This means that when you use the initialize other sensor and distance sensor, this name that you input right here is this name that you see right here and right here. The second thing we can adjust that may be of relevance is the sensor's position, which is this translation feature right here. So this translation feature is relative to the robot. So right now our distance sensor is smack dab in the middle of our robot, and we can change this by moving this. And you can see that the distance sensor moves up 1 meter. There is no graphic as of right now for the distance sensor, so you can just assume that the distance sensor is at the center at the crossing point of these 3 axes. I'm going to change this back to 0. The second thing, probably the more important thing you may be worried about, is the direction of the distance sensor. And you can use these features or these parameters to modify the direction that your distance sensor is facing. This uses axis angle notation, and if you don't understand or know how to use axis angle, easier way is probably just to use this rotation button. So I can just rotate it, and now it will be facing, oops, one more time, forward. The red arrow will tell you what direction that the distance sensor and the other sensors are facing. So for example, the light sensor, direction also matters. So always refer to the the red arrow to tell you what direction the sensor is pointing in. So now we have a distance sensor that's facing forward, and you can change it from there. You can have it change to the side, look to the side. You can have it look up by rotating this blue axis, and now the red arrow is facing up, etc. And you can change these properties for all the other sensors. So let's say my GPS, I want my GPS to be moved out to the side instead. And I can just drag along my GPS. Again, there's no graphic, but you can assume that the GPS is at the crossing point of these 3 axes markers. So those are all the features that we're going to cover in today's tutorial. We covered motors, we briefly covered delays, and we also covered the 4 of the sensors that the robot comes with. There are many more features to both Webots and Webots-Blockly, and to learn more about these features, be sure to check the documentation that will be listed in the description. Thanks for watching the tutorial, and have a good week.